Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on states of matter, and I hope you are enjoying this course with me. Today we begin with lecture 21 from the course, but make sure you watch the previous ones before doing this one. In the last lecture, we learned what is the Graham's law, and I hope the concept is now clear to you that under similar conditions of pressure and temperature, the rate of diffusion of a gas is going to be inversely proportional to the square root of the density. Right, and based upon this law we did a lot many derivations, so I hope all those derivations they are clear to you. In case you still have any doubt, well, they're going to become very clear to you today, because now we are going to do a few problems based on the law. So this will help you clear your concepts very well, and also at the same time help you understand how you're going to tackle various problems related to the law, because this is going to be very important for your examination. Many questions, if you look at the previous year examinations of JEE Mains, Advanced as well as NEET, you will be seeing that many questions they are coming from this topic. So let us begin our learning today with lots many problems on the Graham's law. So the first question is that the relative rate of diffusion of two gases A and B, they are found to be 0.3 and 0.2 respectively. If the density of A is 4, find the relative density of gas B. So the relative rate of diffusion of two gases is given to us. The density of one gas is given, and we have to find out the density of the other gas. So this is very direct application of the Graham's law itself that we have according to the Graham's law. Ra, the rate of diffusion of gas A, divided by Rp, the rate of diffusion of gas B, to be equal to under root of dP by dA, where d is the density of a gas. Right? So you're just going to simply put the values they are given to you, and you are going to find out the relative density of gas B is going to come up to 9. Right? I hope this is very simple, direct application of the law itself. So the next question we have is the rate of diffusion of an unknown gas and chlorine. They are in the ratio of 6:5. Assuming the density of chlorine to be 36, calculate the molecular weight of the unknown gas. So again, the rate of diffusions they are given to us, and density of one gas is also given. So we can apply the Graham's law that RCl2 by R of the unknown gas will be equal to under root of the density of the unknown gas divided by the density of chlorine. So putting the values, you will be finding out that the density of the unknown gas will come up to 25. But what you have to find out is not the density of the gas, but you have to find out the molecular weight of the unknown gas. But we, from our knowledge, that we have revised well, I would say, in the Graham's law, because you'd already learned the concept in this course on some basic concepts. So we know that the vapor density of a gas, if we twice that, multiply that by 2, we will be getting the molecular weight of the gas. So we will multiply 25, the density of gas, with 2 to get the molecular weight of the gas to be 50. Right? So I hope, again, a very simple question. You just have to remember the facts that we learned in the last lecture. So the third question is 180 ml of a hydrocarbon diffuses through a porous membrane in 15 minutes, while 120 ml of sulfur dioxide under identical conditions diffuses in 20 minutes. Calculate the molecular weight of the hydrocarbon. Now what is given to us over here? We are given here a gas which is a hydrocarbon and the other gas which is sulfur dioxide. Okay, and we are given volume of the gas that is diffusing in given time. And what is this? Well, this is going to give us the rate of diffusion of the gas. The volume diffusing over the time taken for diffusion, that is the rate of diffusion of the gas. So if we say that the rate of diffusion of the hydrocarbon is R1, then this R1 is going to be equal to 180 ml divided by 15 minutes, which will come up to 12 ml per minute. Similarly, the rate of diffusion of sulfur dioxide, if we call that to be R2, R2 is going to be equal to 120 divided by 20, that will be 6 ml per minute. So now we have got the rate of diffusion of the two gases. Okay, one is 12 ml per minute, the other is 6 ml per minute. So according to the Graham's law now, we know the relationship of the rate of diffusion to the molecular weight of the gases. So R1 by R2 is going to be equal to under root of M2 by M1. Now when you're going to put out the values, you already know the molecular weight of sulfur dioxide. So you can find out the molecular weight of the hydrocarbon. And this you're going to find out to be 60. Right? Again, very simple questions. All you have to understand is what all we learned in the previous lecture. If all those concepts are clear to you, well, the questions are going to be very simple. The next question we have is 10 ml of sulfur dioxide diffused through a porous plug in 18 seconds. In what time will 10 ml of helium diffuse through the same porous plug at the same temperature? So again, what is given to us is volume in a given time, which will give us the rate of diffusion. So the rate of diffusion of sulfur dioxide will be 10 by 18 ml per second, and the rate of diffusion of helium, the volume is given and we have to find out the time. So that will be 10 by T. So again, according to the Graham's law, we can put the R1 by R2 equal to under root of M2 by M1. So the rate of diffusion of sulfur dioxide divided by the rate of diffusion of helium, which is given to us as 10 by 18, that will be divided by 10 by T. So this will come as 10 by 18 into T by 10. And this is going to be equal to under root of MHE by MSO2, because the masses of these two gases, they are known to us. We do not know the density, but the molecular masses we know. So we can just simply put them and then we will be able to find out the value of T, and the value of T is going to come up as 4.5 seconds. Okay. Now, one thing more which you can remember from what you have learned while we were doing the law last lecture was a direct relationship between the time of diffusion to the density and the molecular masses when the volume is same. Okay. So this is something that we learned in the last lecture as well, that if the volume that is diffusing out is the same, which we have over here to be 10 ml and 10 ml, so the volume diffusing of the two gases is same. So you could directly put this over here as well, and this would have saved you time. I have done it completely so that in case you do not remember the formulas, we are going to be many that you are going to learn during the course of your learning. So even if you forget, there is nothing to worry, you can do it completely. But if you remember it directly, well, this is going to save a lot of time for you people. Okay, so I hope this is also clear to you, that you could have just simply put T1 by T2 equal to under root of M1 by M2 and you would have got your answer in a fraction of a second. The next question we have is 32 ml of helium effuses through a fine orifice in 1 minute. Then what volume of CH4 will effuse in 1 minute under similar conditions? So here you can understand first of all the difference between effusion and diffusion. The previous question you have seen the gases diffusing through a porous membrane, and now you are using the term effusion through a fine orifice. So the diffusion process, you can say, that is taking place through a very small hole is what we call as effusion. Right? So I hope this is clear to you now with this example as well. So we have helium and methane gas effusing under similar conditions, and the Graham's law is going to be just applicable to the process of effusion, just like we have it for the process of diffusion. So what we know is that the rate of effusion, just like diffusion, is going to be proportional to 1 by under root of m. Right? And also we know that the rate is going to be equal to the volume effused over given time. But here again, just like the previous question where volume was equal, now what you can see is that the time is the same. Right? So here the time is same. So what we are going to get is when we are going to put R1 by R2, just let me put it down. Yes. So this is what we have learnt in the previous lecture, that R1 by R2, this is equal to V1 by T1 divided by V2 by T2, right? So here what we have is that the time is same. So this is going to cancel out. So R1 by R2 is going to be equal to V1 by V2. So we can directly put that VCH4 over VHE. This is going to be equal to under root of MHE over MCH4. And then it is going to be very simple. You have to just put out the values. You will be getting the volume of methane gas if using out in 1 minute to be 16 ml. Okay, so if you directly remember the relationship of the volumes when the time is same, or the relationship of the time when the volume is same, well, it is going to not take you more than a fraction to solve the question. The next question we have is that a mixture of H2 and O2 in 2:1 mole ratio is allowed to diffuse through an orifice. You could have written this as a fusion as well, right? So a mixture of H2 and O2 in 2:1 mole ratio is allowed to diffuse through an orifice. Calculate the composition of the gases coming out initially. Now here, let the number of moles that we have taken of the two gases to be N1 and N2, and this N1 and N2 is given to us as 2:1 ratio, okay? And the number of moles of the gas which is diffusing out to be N1 dash and N2 dash. Since the gases, they are fusing from the same container, they are kept at the same temperature, right? So the temperature is going to be the same, as well as the volume of the gases initially we had taken, that was the same because they were in the same container. So when volume is same, temperature is same, but the number of moles are different, what we are going to say is, well, the number of moles of the gas is going to be directly proportional to the pressure that is being exerted by the gas. So this means that the pressure being exerted by the two gases, that is different. And when the pressure is different, what we have as the rate of diffusion or a fusion, well, this is going to even depend upon the pressure of the two gases. So R1 by R2, this is going to be equal to P1 by P2 into under root of M2 by M1. Again, this is something that we have learned previously in the last lecture as well. So I hope now this is clear to you with this example. So what we can write this is that P1 by P2, as this is going to be proportional to the number of moles, so we can replace it by N1 by N2. So R1 by R2 is equal to Ny by N2, which was the initial number of moles of the gas we had taken in the container, into under root of M2 by M1. But now this rate of diffusion or a fusion, this is going to be proportional to the number of moles of the gas that is effusing or diffusing out. Okay, so we can say that R1 by R2 is going to be equal to N1 dash by N2 dash. So we are going to replace this by N1 dash by N2 dash being equal to N1 by N2 into under root of M2 by M1. Now it is going to be very simple. What you have to do is just put the values. You know the molecular masses of hydrogen and oxygen gas. You know the initial number of moles that we had taken. So the composition of the gas that is going to come out is going to be in the ratio of 8:1. Okay, so I hope this is clear that the number of moles of the gas which we had taken initially was proportional to the pressure the gases they were exerting. And because the pressure conditions were not the same, we had to put this P1 by P2 into, because the rate of diffusion is going to be directly proportional to the pressure exerted by the gas. Right? So I hope this question is now clear to you, and what we have learned previously in the last lecture, the concept has also become clear with this question. The next question we have is 1 mole of nitrogen gas at 0.8 atmosphere take 38 seconds to diffuse through a pinhole, whereas 1 mole of an unknown compound of xenon with fluorine at 1.6 atmosphere take 57 seconds to diffuse through the same hole. Determine the molecular formula of the compound. So again, what you are given is the time for the diffusion to take place, as well as the different pressures of the two gases. Okay, so when the pressure is different, we are going to apply the formula just like we did in the previous question. The rate of diffusion would be equal to R2 by R1 equal to P2 by P1 into under root of M1 by M2. Well, I've just written the reverse order R2 by R1 because I wanted to write T1 by T2. If you are not specified the volumes of the gases, well, this would be an assumption that the container which you have taken during the experimental conditions, that is the same, or you can say that the volume of the gases is going to be the same. Okay, so we will be having the volumes to be cancelling out and the rate being inversely proportional to the time for diffusion. R2 by R1 would be written as T1 by T2. Okay, so you could have written R1 by R2 equal to T2 by T1, or I have written R2 by R1 equal to T1 by T2 because the volumes, they are going to be the same. So we have T1 by T2 equal to P2 by P1 into under root of M1 by M2, or you can write from this the value of M2 to be equal to P2 into T2 divided by P1 into T1 square multiplied by M1. So from here you can find out the molecular mass of the compound of xenon with fluorine to be 252 gram per mole. Okay, this is, I think, very clear, very simple thing. The molecular mass of nitrogen gas you knew, and you have now find out the molecular mass of the other gas. Now, what we do not know is the molecular formula of the compound of xenon with fluorine. So we can write that as XeFN. And from here, the mass of xenon plus the mass of fluorine into n number of atoms of fluorine in the compound, this is going to be equal to 252. Just put out the values. What you will be finding out, the value of n is going to be approximately equal to 6, and therefore the molecular formula of the compound is going to be XeF6. Right, so I hope this is also clear. Now you have a better understanding where you're going to use this formula. The last question that I have for you today is that through the two ends of a glass tube of length 200 centimeter, HCl and ammonia gases, they are allowed to enter. At what distance ammonium chloride will first appear? So again, this is something that we have already done in the previous lecture, a thorough understanding of the concept that when we have a same tube, through one end one gas is coming and through the other end the other gas is coming, so the rate of diffusion is going to be proportional to the distance they will be traveling. So supposedly we have HCl gas coming from one end and ammonia gas coming from one end. The point we are going to meet is going to be the formation of ammonium chloride, and this will be visible as a white cloud. And the rate of diffusion, as this is going to be equal to the length they are traveling, so we can write that R NH3 by R HCl is going to be equal to L NH3 by L HCl. And the rate of diffusion, you already know that it is inversely proportional to the square root of the molecular masses. Why we have taken this relation is because the molecular masses, they are known to us. So we can put those values to find out the relative rate of diffusion of the two gases, and this is going to be 1.465 by 1, the rate of diffusion of ammonia to that of HCl, and this is going to be equal to the distance they will be traveling. So what this means is that as the distance traveled by a gas is directly proportional to the rate of diffusion, and ammonia, we can see that it is traveling 1.465 times faster than HCl. Therefore, ammonia gas will travel 1.465 centimeter in the same time that HCl will travel 1 centimeter, right? So ammonia is traveling faster, it will cover a greater distance. So the ammonium chloride cloud will be formed closer to the HCl end. Okay, so I hope this is clear. So now as the length of the tube is 200 centimeter, we can write that if this distance that HCl gas is traveling is D, and the distance ammonia gas will be traveling will be 200 minus D. So you will be putting the length of ammonia to be 200 minus D and the length of HCl gas, that is the distance traveling, to be D. So from this you will be finding out the value of D, which is going to be the distance traveled by HCl gas to be 81.13 centimeter, and the distance traveled by ammonia gas to be 118.87 centimeter, which is 200 the length of the tube minus the distance traveled by HCl gas. Fine, I hope this is clear. So ammonium chloride will be formed first at a distance of 81.1 centimeter from the HCl and 118.9 centimeter from the ammonia end. Right? So this is as far as a collection of questions that I had for you to understand the concept that we have learned. And in case you still have any problems, please do put them in the comment section, or you can put in the email, that the email ID is going to be just provided you on the last slide. And you can also join us on the Facebook page of the channel. The Facebook page has the same name as the channel itself, that is H2O Chemistry. So that would be all for this lecture, and the next lecture again is going to be a very important lecture where we would be understanding the kinetic theory of gases. So in case you have not subscribed to the channel till now, please do that, because only then you will be getting a notification the moment we put up the next lecture for you. So please do subscribe to the channel, and also if you've liked this lecture, you have learned a lot, you have gained a lot, please do click on the like link before leaving. Thank you and have a nice day. God bless you.